Now, to get a gist of what time dilation is, suppose we have an suppose we have someone in the spaceship, and then he shoots a flashlight. He shoots a flashlight, and it goes up and then goes down. So the distance between his hand, let's say, and the mirror, let's say it's a distance d. Let's say the distance between his hand and the mirror is a distance d. So this this mirror, this light travels a distance 2d. So the total time for the event would be total time for this event would be so the total time for this event would be 2, because it travels 2 times the distance, 2d divided by the speed of light, because this flashlight is moving, the light in the flashlight is moving at the speed of light, of course. And we also know that the speed of light doesn't change in any reference frame. So so the total time for this event would be for the person inside the spaceship would be change in t equals 2d divided by c. Now for the person outside the spaceship, for the total person now for the person outside the spaceship, he doesn't see the light just go up and down. He sees the light go like at an angle upwards, and it hits the top of the mirror, and then goes back at an angle. Goes back at an angle. Goes back at an angle like this. So so we could so we could write it so we could write we could write this distance, since is this distance the same as the distance from the person's hand to the mirror. We could write this distance to be d. We could write this distance to be d, and we could write the distance from this top, from here to here, which is half the cycle, to be c change in t divided by 2. Now, as we said from before, the distance for half the cycle would be c change in t over 2, because for the person outside the spaceship, he sees the light still traveling at the speed of light, but then for the whole cycle, which is this plus this, would be c change in t. That will be the total distance, the the to, the speed multiplied by the total time. But since we're only observing this part, like half the distance, we say that c change in t divided by 2 would be the distance traveled for half the speed of light. Would be distance traveled for half the cycle. So since in this spaceship, this guy is moving with constant velocity inside the spaceship, uh, he has his own inertial frame of reference. But this guy, since he's outside the spaceship, and then he's outside the spaceship, for his inertial frame of reference, this we have to incorporate the speed of this spaceship. If that makes sense. V, the velocity of the ship, would be v, the velocity of the ship, times v, the velocity of the ship, times change in t, velocity of the ship times change in t, and divided by 2. Okay, so and divided by 2, divided by divided by 2. Okay. Now, just from intuition, we could see that for the observer outside the spaceship, the speed of the light takes, since it travels a much longer distance for it to like hit the top of the mirror, then reflect back, than just this scenario where the light just hits the mirror like vertically and then bounces back vertically. We could see that the time slowed down uh time slowed down outside for the observer seeing the spaceship. So Now, for the observer outside the spaceship, see that the observer's time is much faster than than the guy's time inside the spaceship, as can be seen by the observer outside the spaceship. So for him, the light takes much longer for it to hit the mirror and bounces back and goes to the floor. So time slows down for him for the spaceship. In his inertial frame of reference, he sees time slowed down inside the spaceship, sees time slow down in spaceship, and his time runs normally. And then for this guy, he sees his time run normally, and this guy's time run slower, because for him it's as if he's stationary and he's moving, and for him it's as if he's stationary and he's moving. So you could see the paradox here. So let's move on with the derivation for the time dilation. Uh, so we could so we know that for half the cycle, for the observer outside the spaceship, he sees he from the floor to the top of the mirror, the distance traveled would be c changing t divided by 2, and then for the velocity of the spaceship, the distance traveled after changing t, because of the velocity of the spaceship, would be v changing t divided by 2. And then this is just the distance. This is just the distance from the floor to the top of the mirror, which is d. So using the Pythagorean theorem, we could write the following. Now from Pythagorean theorem, we generate this equation over here, and then this is the distance. This distance is the same as this distance, which is the distance from the person's hand to the mirror. And if you replace this distance in this equation with change in t prime times t divided by 2, and then change in t prime is basically the change in time for the event for the person inside the spaceship to see the light go from the top of the mirror and back down. If you replace this uh, formula into this, we will generate an equation. And now you could cancel the 4's on both sides of the equation, so you could cancel these 4's, and that will give you this equation. And that will give you this equation. And now you could isolate for t prime, which is the time inside the spaceship, and you will get, after rearranging the equation, you could divide c squared by both sides. So you divide this by c squared, divide this by c squared, divide this by c squared, and you will get. Now you could factor out change in t, which is the time for the outside observer, and you will get. Now you could square root both sides, and you could, like this, square root this side and square root this side to get t prime, which is the time inside the spaceship. And then after that, you will get square root both sides, you will get this equation. Now if it makes you happy, you could divide both sides by the square root of 1 minus v c squared to get and these are the two equations that you get that relate this change in time, the total time or total event for the outside observer, and then the total change in time for the person inside the spaceship. Now notice that the time for the outside observer, the time is dilated by a factor from the original time inside the spaceship. The time is dilated by a factor of 1 over 1 minus v squared over 1 minus v squared over c squared. So you could write that gamma, which is the time dilation, equals. Now notice that the time dilation gamma equals 1 over 1 minus v squared over c squared, and that this factor is always greater than 1, because v squared, when considering that v squared is not equal to 0. And notice that when v squared, like the relative speed is significantly less than the speed of light. squared, then gamma could be approximately equal to 1, and you have no relativistic time and no relativistic momentum and stuff. Okay, now from this equation, you can also see the faster the spaceship moves, the faster the spaceship move, or the closer the spaceship velocity reaches the speed of light, the slower the time inside the spaceship gets from this equation, as you can see from this equation.